In the previous video, we computed the self-inductance of a toroidal coil based on the approximation that the toroid was thin. In other words, that the cross-sectional width of the toroid was small compared to the radius. Now in this video, we're relaxing the thin toroid approximation and computing the self-inductance of a thick toroidal coil, and this is going to require an integral for the flux calculation. So just a quick description here on this toroid. It has rectangular cross-section of height h, and the inner radius is a, measured with respect to the center of the toroid, and the outer radius is b, measured with respect to the center. This means the width of the cross-section is b minus a. We've put a current of little I running through the coil in the direction that would yield the counterclockwise magnetic field when the torus is viewed from above. And we've assumed that the current is increasing at this moment in time. Remember, we won't see induction effects unless that current is changing. So to get started on the self-inductance calculation, we go back to Faraday's law. And Faraday's law says the induced EMF is the negative of the time rate of change in magnetic flux through the turns of the coil. And this can also be expressed as the number of turns multiplied by the rate of change in flux through one turn of the coil. Next, we get a quick reminder of the definition of self-inductance. And the idea here is that the induced EMF is going to be proportional to the rate of change in current in the coil, and that constant of proportionality is what we're after. That's the self-inductance of the coil. So the plan is to do the Faraday's law calculation and then show that the induced EMF is proportional to the rate of change in the current, and then the constant of proportionality is exactly what we're looking for. Now first we need to get a quick reminder before we start grinding on Faraday's law. We already found that the magnetic field in a toroidal coil is circumferential, and using Ampere's law, we found that the magnitude is given by mu naught Ni over 2 pi r, where N is the total number of turns in the coil and R is the distance from the center of the toroid. So this is critically important to absorb before we do the calculation. This magnetic field is getting continuously weaker with distance from the center, and this means the flux calculation is going to require an integral. So we'll just grab our cross section real quick and we move to a little more schematic view of things. We're just looking at that rectangular cross section, and our magnetic field is into the page here, providing flux through one turn of the coil. But remember that field is getting weaker with distance from the center of the toroid. This means that to calculate flux, we can't just use B times A for the entire cross-sectional area. Instead, we have to slice the area into thin vertical slices of width dx. And on one of these thin slices, the magnetic field is constant because we've constrained the area to one exact value of distance from the center, and we call that distance x. So we proceed to find the flux through a single turn by slicing into thin ribbons. So we can say d phi, the incremental flux for one turn, is given by b of x multiplied by dA. Again, that b of x is just reminding us that the magnetic field strength is actually a function of x here. And the little dA, that's the area of that infinitesimal little rectangle shown in the diagram. So now we can put in the details about b of x and dA. And we get mu naught big Ni over 2 pi x for the magnetic field. Remember that big N is the total number of turns in the toroidal coil. So that's just our magnetic field from our previous Ampere's law result. And then for dA, this little rectangle just has an area of width times height, so that's going to be h dx. So now we're going to add up all these incremental flux contributions using an integral. So we can say that phi for one turn is the sum of all the d phi's through this one turn of the coil. And that's just an integral acting as a summation device for adding up infinitely many infinitesimal contributions. So now we put in the details about our d phi, and we'll pull the constants out of the integral as we work. So we pull out all these constants, mu naught big N I h over 2 pi out in front. And the only piece in this expression that had x dependence was the 1 over x. We had an x in the denominator for our magnetic field. So we're taking all those constants out in front and multiplying by the integral of 1 over x. And notice there that the limits of integration for x are from a to b as we cover this area in thin rectangles from left to right. Okay, so we're left with the integral of 1 over x, and that's easy enough. It just integrates to the natural log of x. And when we evaluate that across the limits of integration, we're going to get natural log of b minus natural log of a, but using log properties, that's just natural log of b over a. So now we have the flux computed through a single turn of this toroidal coil, and it turned out to be mu naught big N IH over 2 pi times the natural log of B over A. And now we're going to go back to Faraday's law, remembering that the end goal here is to relate the induced EMF to the time rate of change in the current. So there's our expression of Faraday's law. The induced EMF is negative big N for the total number of turns in the coil times the time rate of change in the flux through one turn. So we simply plug in the flux through one turn that we just computed, and we have the time derivative of all that stuff. But the only time-dependent quantity in those parentheses is the little I itself, the changing current in the coil. So we can pull out all those other constants. And this gives us a negative mu naught big N squared times H over 2 pi natural log B over A times the time rate of change in the current. But remember, the whole definition of self-inductance is that it's the constant of proportionality between the induced EMF and the time rate of change in the current. So all those constants out in front is exactly what we're looking for here. That's the self-inductance of the thick toroidal coil, mu naught N squared H over 2 pi times the natural log of B over A. This video is the last in a short series on electromagnetic induction, and you can find links to all the videos down in the description. I've posted a link to the first video in the series about mutual inductance at the lower left, and at the upper left you'll find a link to the previous video where we derived the inductance of a toroidal coil based on a thin coil approximation. I also want to invite you to check out zaxlabphysics.com to see this entire physics course laid out into the modules that I actually use to teach the class. This is a much cleaner organization than you can get from YouTube playlists, and I've put a link to my website in the description as well.